we introduce peer cache, Scaleout I/O, that delivers extreme file performance. This is a standard Intel strategy to blur the lines between file I/O and memory I/O. So we use NVMe, but instead of building file systems out of NVMe, we make your local file system look like a cache, right? And we provide a shared storage model for that cache using peer-to-peer. So this enables high-performance compute in the cloud for EDA tools. And by using peer-to-peer between multiple readers and writers, we can now do everything in parallel. Right? Most file systems today that we're using are serialized. There are alternative parallel file systems that have been used in HPC compute for a while, but they've been optimized for different kinds of workloads, which is typically high concurrent I/O, which is not the way EDA works. So what we do is that we use flash as a cache, not as a storage. And it slashes your costs because using small 1 terabyte or 2 terabytes of NVMe per node, you can now get extreme file performance. We offer 3 simple steps to hybrid cloud bursting. And some people have said to me, wow, I don't believe this. And I tell you, if you don't believe it, come upstairs to booth 2618. We've got a nice car there for you to look at, and we'll show you how this occurs and how quickly it occurs, right? You simply, on one of your compute nodes, register your filer mount points and your namespaces to a little agent. That agent then allows you to project your entire corporate data, right, in the cloud. So you type ls, and every mount that exists, everything that you've registered on the left-hand side is suddenly available. And it doesn't take very long because we only transfer the data on demand. So the first ls is just the top level. The second ls is a little bit deeper. You can do a recursive, and it just pulls it all on demand. Once the virtual environment's been created, and the reason you create the virtual environment is so the application sees everything that it needs. It sees its includes, it sees its configuration files, it sees all the things it needs to see, right? But they're all virtualized. And as they're accessed, we pull them over the wire. What we're able to do is to really provide a scale-out solution for I/O because we're bringing files to the local compute node. We are not going over the network to create a remote file system. We are bringing those files locally through this on-demand caching onto the local NVMe. This gives you a lot of I/O. In fact, more than you know what to do with, right? A standard, Amazon instance, for example, with 2 NVMEs can give you 2 gigabytes per second of I/O. And something like a C5D 18x large can give you 10 gigabytes. Guys, this is per node, right? So unlimited aggregate throughput, this is true scale out. But more importantly, it's very, very cheap because we're not storing your data there. It's transient. We have the job, we run the job, and we get another job in there, right? And storage happens in the background. We're very, very heavily focused on job throughput, job execution, and speed of completing these jobs. Storage is something that happens in the background asynchronously, and we can write it back to wherever you want. We don't care. We're totally agnostic to it.